Okay, here we have a situation, hypothetical situation, where we have some mass m1 of a substance. Okay, we know that mass. It'll be so many kilograms or so many grams. At temperature T1, and let's assume that the object is hot. And we've got some water here. Mass m2 of water, temperature T2, and the water is cold. We're going to put the mass m1 into the water, and we're going to assume that there's no thermal energy exchange with outside, that the mass is going to exchange its energy with the water very quickly, or that the system is well insulated. But when we put the mass into the water, being at a higher temperature, its molecules have greater average kinetic energy. The molecules of the water have lesser average kinetic energy, so that when the molecules of the water vibrate against the molecules of the solid lose kinetic energy, and the molecules in the water gain kinetic energy. Now if mass m1 is going to lose thermal energy, and that thermal energy will be gained by the water. Again, we're assuming that this is a closed system, that there's no dissipation of thermal energy outside the water and the solid. Okay, so we have a mass m2 of water, temperature T2, mass m1, T1. We put them together, we get a mass m1 of the substance and a mass m2 of the water, and after a time, after all the thermal energy has been exchanged, they'll all be at the same final temperature, which we'll call T sub F. And we'll note that T2, the cold temperature of the water, will be less than TF, and the TF will be less than T1. That is, the final temperature will be between the original temperature of the water and the original hotter temperature of the mass. Okay, so the water will gain energy, delta Q of water, which will be m2, the mass of the water, times the delta T of the water, the number of grams, and the number of degrees Celsius, for example, multiplied by the specific heat, which we just discussed in the previous problem. The specific heat of water is 4.19 joules for every gram in Celsius degree. So to raise 1 gram of water by 1 Celsius degree requires 4.19 joules. If we then multiply that by the mass of the water, we'll get the number of joules per Celsius degree, and then times the delta T, we'll get the number of joules of energy change. Okay, now the delta T of the water is, of course, the temperature it attains minus the temperature it started at, TF minus T2. So this is an expression for the thermal energy gained by the water. The substance loses, it loses energy, m1, which is its mass, times its specific heat, which we'll call C1, times the T1 minus TF. Okay? Now T1 minus TF, T1 is higher than TF, so this is a positive quantity, so it loses a positive quantity. Now its change in thermal energy, of course, is negative and will be the negative of this quantity, which is m1 C1, and we switch the TF and the T1, that'll change the sign of everything and give us a quantity less than 0. Okay, it loses this, its change is this. The net change in thermal energy in a closed system has to be 0. So the delta Q of the water plus the delta Q of the substance has to be 0. And that means that the M2C2 TF minus T2, the change of the water, this expression, which we write again here, plus the delta Q of the substance, which is this expression, which we write here, is 0. In the given problem, we know the two masses, we know the specific heat of the water, we know the final temperature and the two initial temperatures. The only thing we don't know is C1, so this is an equation that can be solved for C1. And that's the strategy we use in solving this problem.